Hello friends, today we are going to see some remaining topics in multithreading. We were viewing the example of creating multiple threads in the last session. We will again take that example. That example was creating class new thread implementing runnable interface. There is one string called string name, thread T. Then name is initialized to this parameterized constructor's thread name. Then new thread is created and then started this thread. Now run method is called implemented here for 5 times for each and every 1 millisecond 1 seconds gap, 1000 milliseconds gap. This name will be printed and interrupted in exception is also handled. Then in multi-threaded demo program we are creating 3 separate threads, 1, 2 and 3, and for all other threads to end, we have to wait for 10,000 milliseconds, that is 10 seconds. And then after all threads has been ended, we will call main thread interrupted and main thread exiting. Now this is the output of this program. New thread, thread 1, 2 and 3. This is the group name, thread group name main, and this is the priority provided. 1, 2, 3 is called 5, 4, 3, 2, 1. And after that 1 and 2 and 3 will exit, and then at last main thread will exit. Okay, now as you can see, once started, all three child threads share the CPU at the same time to run concurrently. Call to sleep 10,000 millisecond, that is 10 seconds. Why? Because we have to wait till all the threads has been ended. And this causes the main thread to sleep for 10 seconds, ensures that it will finish the last and handle all the shutdown operations. Now we will see is alive and join. These are the very special functions provided by Java to handle the situation like main thread has been ended. As mentioned, often you will want the main thread to finish last, and not every time you can guarantee that. In the previous examples, we provided the sleep method, and that sleep method was causing the main thread to exit last. But this will not be efficient for all the programs, like many more threads are running like a child thread and only one main thread, and you have to calculate all their finishing time, and after all those threads will be finishing, main thread will be finished, and this is very time consuming process to exit the main thread as the last thread. And to ensure that all threads terminate prior to the main thread, we were using the sleep method. This is hardly satisfactory solution, and how can one thread know when another thread has ended? So this is the main question that is raised. Thread provides a means by which you can answer this question. Two ways are there to determine whether a thread has been finished or not. You can call is alive on thread. This method is defined by thread class, and its general form is boolean, final boolean is alive. This is alive method returns true if the thread is still running and you have to wait. Otherwise it will run false. Okay, so you can call it like thread dot is alive. It will tell you if it is true, means the thread is still running, it is still alive, and if it is returning false, means it is not alive, has been ended. While is alive is occasionally useful, the method that we will more commonly use to wait for a thread is to finish is called as join, shown here. Final void join throws interrupted exception. This method waits until the thread on which it is called is terminates. Okay. This join method is very important than is alive method because it waits until the thread on which it is called is terminates. Its name comes for the concept of calling thread waiting until the specified thread joins it. Calling thread will be waiting until the specified thread joins it. Additional forms of join allow you to specify maximum amount of time that you want to wait for the specified thread to terminate. Here is an improved version of the preceding example that you join to ensure that main thread is the last to stop. Okay, so we will see here with isAlive method also and join method also, using join to wait for the threads to finish. Class new thread, we are implementing again runnable interface. We are seeing all the examples that will implement the runnable interface. We are not extending thread class here. String name thread T, then it's a parameterized constructor. New thread has been instantiated, then it will start. Then public void run is implemented same way as the previous example. Thread.sleep for 1000 millisecond, that is 1 second, and interrupted exception is caught. Now 1, 2 and 3. 3 threads are created like the previous example, and we are checking if it is alive. Object 1 dot, this is object 1 dot T. Object 1's T will be here, the thread object. First object's thread object dot isAlive. So this way we are calling the isAlive method. Then object 2 dot T dot isAlive, object 3 dot T dot isAlive. It will return true or false depending upon the thread is exited or not. Now waiting for the threads to finish. Object 1 dot T dot join, the same way we are calling isAlive, the same way we are calling join method over here. And here also we are catching the interrupted exception. Thread 1 is alive, thread 2 is alive, thread 3 is alive, and main thread exiting. Okay, so now 3 thread has been created. Thread 1 is alive, true, it is still running, 2 is still running, 3 is still running. Waiting for the threads to finish. Okay, so here we have called the join method. What is the use of join method? Join method waits until the thread on which it is called terminates. Okay, so join method's work is what, task is what, it has to wait, and its names come from the concept of calling thread waiting until the specified thread joins it. Okay, so here it is waiting for the threads to finish 1, 2, 3, then 1, 2, 3 up to 1, then 2, 3 and 1 is exited. This sequence is dependent upon the compiler that on which you are running your program, okay, or the processor speed. It is not compulsory that first 3 will exit, then 2 will exit and 1 will exit. This sequence may change. Thread 1 is alive, false, thread 2 is alive, false, and thread 3 is alive, false, and then main thread will exit. Here we have not seen any output related to join, because what is the work of join? Its work is only to wait until the specified thread joins it. Okay, as you can see, after the calls to join return, threads have stopped executing. Okay, after the waiting time is finished, threads on which the join is called, they stop execution. Okay, now we will see thread priorities. Thread priorities are used by the thread scheduler to decide when each thread should be allowed to run. Okay, like we have seen in short, what are the thread priorities, the higher priority threads and lower priority threads, and what to be done when equal priority threads are running concurrently. Okay, in Windows operating system, if equal priority threads are fighting for the CPU, what they will do, they are provided CPU time in round robin fashion, and for others they should give the other threads CPU by mutual understanding, otherwise other threads will not be run. And for whatever reason, if the lowest priority thread or lower priority thread has been acquired the CPU, and if higher priority thread is coming, it must relinquish the control from CPU, no matter what, no matter if it has been ended with the execution or not. Okay, so this way we have understood at the start of this session, this chapter. Now we will see in detail what are the thread priorities. And this thread priority will tell the scheduler that when each thread should be allowed to run. High priority threads get more CPU time than lower priority thread. In practice, the amount of CPU time that a thread gets often depends upon several factors besides its priority. For example, how an operating system implements multitasking can affect the relative availability of CPU time. Okay, so only priority is not important thing. If your operating system, how your operating system is implementing multitasking, like in Windows operating system, in Ubuntu operating system, how they are operating a multitasking or implementing a multitasking operation can affect the relative availability of CPU time. Higher priority thread can also preempt a lower priority 1. When a lower priority thread is running and higher priority thread resumes from sleeping or waiting on input output, it will preempt the lower priority thread. Threads of equal priority should get equal access to CPU, but you need to be careful. Java is designed to work on wide range of environment because Java is used worldwide. So there can be many more types of working environment in overall world. So you should be careful while operating upon the priorities of threads. Some of those environments implement multitasking fundamentally differently than others. But threads that share the same priority should yield control once in a while. That means what? If one thread is acquired CPU, it should relinquish the control after some time to the other equal priority thread. This ensures that all threads have chance to run under a non-preemptive operating system, like Windows operating system. Unlike Windows operating system, sir. In practice, even a non-preemptive environment, most threads still get a chance to run because most threads inevitably encounter some blocking situations such as waiting for input output. In some non-preemptive working environments, most threads will still get the CPU time because those threads inevitably encounter some blocking situations such as waiting for input output. Like one thread is acquiring CPU time, and in between it requires the access to input file, like opening a file, reading a file, writing to a file. For that purpose it has to wait, and it is a non-preemptive system, but still if it is requiring access to input output, what it will do, it will relinquish control from CPU and the other thread will enter the CPU. Also, some types of tasks are CPU intensive. Such threads dominate the CPU. For these types of thread, you want to yield control occasionally so that other threads can run. So, a working environments are not same. Okay. Some type in some non-preemptive system, some threads will still get a chance to run in other types of systems. Some types of tasks are CPU intensive, and such threads will dominate the CPU. To do not dominate the CPU, what it should do, it should yield the relinquish the control occasionally so that other threads can run. To set a thread priority, use set priority method, which is member of thread final void set priority integer label. This is the final method. Label specifies the new priority setting for the calling thread. The value of label must be within the range min priority and max priority. So priorities are given as a constant in Java inbuilt. So they should be within the range from 1 to 10, minimum priority and maximum priority. These values are 1 and 10 respectively. And non-priority is a 5, normal average priority. To return a thread to default priority, specify non-priority, that is a default priority. These priorities are defined as a static final variables within a thread class. Those are inbuilt. You should not modify it. Why? You should get it without using object, so that those are static. You can use it without using object of thread class. For that purpose, they are declared as static. You cannot modify them. For that purpose, it is declared as final, and those are variables. But still, but since they are final, you cannot modify it. You can directly use it like min priority, min underscore priority, max underscore priority, and norm underscore priority. You can obtain the current priority setting by calling the get priority method of a thread. So what is the method? Final int get priority. Final void set priority, integer level, and final int get priority. It will return the priority. Implementations of Java may have radically different behavior when it comes to scheduling. Okay, scheduling will be different on different Java, on different working environments. Okay, so what are the working environments? Windows XP, Windows 98, Windows NT, Windows 2000. Like there are so many types of versions available of only Windows type of operating system, more or less as you would expect. And this in these different types of environment, scheduling will be different. However, other versions may work quite more differently. Most of the inconsistencies arise when you have threads that are relying on preemptive behavior instead of cooperatively giving up CPU time. When there is an operating system, like it is dominating the CPU. One thread is going into CPU and not coming out, and not relinquishing control, and not giving CPU time to other threads those are waiting. This is very much inconsistent. It is very much irritating behavior. Like it is not like mutual understanding between threads. Okay, so in this type of operating system, it is very irritating. The safest way to obtain predictable cross-platform behavior with Java is to use threads that voluntarily give up control of the CPU. So what is the best way or safest way? You have to use threads that will voluntarily or concurrently, after some time, after some milliseconds, they voluntarily give up control of the CPU time, CPU access. So the following example, two threads at different priorities which do not run on preemptive platform on the same way as they run on non-preemptive platform. Okay, so this is the example. One thread is set 2 levels above the normal priority as defined by thread.not priority, and other is set to 2 levels below it. Okay, the threads are stated and allowed to run for 10 seconds. Each thread executes a loop counting the number of iterations. After 10 seconds, main thread stops both threads. The number of times that each thread made it through the loop is then displayed. Okay, now this is the clicker class we have implemented using the runnable interface. Long click 0 thread T, private volatile boolean running is equal to true. Public clicker integer P, T is equal to new thread. So this is the parameter, and this parameter is set as a priority to thread. Okay. So this is the integer number between 1 and 10 we have to pass. It should not be less than 1 and it should not be greater than 10. While running, this is a run implementation. While running, click will be incremented by 1. Click's value is 0. Its long value. Now stop method running is equal to false, and start method, it will start. Thread will start. Now high and low priority. Thread dot current thread. Current thread will return you always main thread, and its third priority thread dot max priority. Clicker high, new clicker thread dot norm priority +2 and -2 below it. Now we will start low dot start and high dot start. First of all, we have started with the lower priority thread. Okay. Thread dot sleep 10,000 seconds. So this will sleep. Main thread will sleep for 10 seconds. 10,000 milliseconds, that is 10 seconds. Interrupted exception is also caught here. After some time, that is 10 seconds, low will stop and high will stop. Wait for the child threads to terminate. High dot T dot join and low dot T dot join. And here also interrupted exception is caught. Now we are printing low dot click and high dot click value. The output of this program shown as follows when run under Windows indicates that threads did context switch even though neither voluntarily yielded CPU nor block for input output. Okay, it was operated on Windows operating system. The higher priority thread got the majority of the CPU time, so that the value generated by high priority thread is higher and the value generated by lower priority thread is lower. What this program is doing, actually we have set the high priority thread plus non-priority, that is 5 plus 2, 7, and low priority, that is 5 minus 2 is equal to 3. So first of all we are starting low priority and then starting high priority. Then again here, first of all high is waiting for join, then low is waiting for join. First of all, low priority thread has been started and low priority thread is stopped after 10 seconds. But still, since high priority is the highest priority, it got the control of CPU most of the times than low priority, so that the value, that is click value, here we are incrementing click value while running, and in stop method we are stopping the running after 10 seconds. After 10 seconds, after stop is called, low will be stopped first, so low's value will be low, and then high value will be high because it is a higher priority, and it is also stopped in the afterwards than lower. Okay, and unless and until the value of running is true, it will increment the click value. But in our program, it is still giving the higher priority thread the highest priority, because in it was working in context switching environment. It neither voluntarily yielded control or nor block for input output, because we have set the priority as 7 and 3. So in this case, high priority thread has been got the majority of the CPU time, and so the click value is very much greater than the low priority thread. The exact output produced by this program depends upon the speed of your CPU and the number of other tasks running in the system. Okay, it depends upon your CPU speed. So each and every person's output may be different. When this program is run under non-preemptive system, that is not relinquishing control cooperatively, different results will be obtained. One other note about the preceding program. Running is preceded by the keyword volatile. Although volatile is explained more carefully in upcoming chapter, it is used here to ensure that value of running is examined each time the following loop iterates. Okay, volatile means value of running is examined in this case while running click plus plus. So running is volatile, running variable is volatile, its value is checked again and again. Without the use of volatile, Java is free to optimize the loop in such a way that local copy of running is created. Okay, so copy will be local if running is not given a volatile keyword. The use of volatile prevents this optimization, telling Java that running may change in ways not directly apparent in immediate code. Volatile tells the Java compiler that running may change, and it may be changing in a different ways, and this way will not be directly apparent in the immediate code. Now we will see synchronization. When two or more threads need access to a shared resource, they need some way to ensure that resources will be used by only one thread at a time. So synchronization is very important thing. You have to understand it. Why? Because synchronization questions are asked many times in interviews. So not only for interviews, but to build efficient Java programs using multi-threading, you have to understand synchronization. You have to understand its theory first. Okay. So what is synchronization? When two or more threads need access to a shared resource. Okay. multiple threads are running and they need access to a one shared resource. They need some way to ensure that there is a mutual understanding about that resource. Only one thread at a time will get the access. And when one thread is writing to, for example, file, the other thread should not halt it immediately in between to read it. Okay. When one thread is completed writing, other thread may read it. One thread is completed reading, other thread should write it. So it is very simple or famous example given related to synchronization. There should be mutual understanding between the thread, and synchronization is it's built depending upon the mutual understanding. Process by which this is achieved is called as synchronization. Java provides unique language level support for it. Java has given a synchronization inbuilt. Okay. Key to synchronization is the concept of the monitor. We have already seen the monitor example. Monitor is an object that is used as a mutually exclusive lock or mutex. Okay. So once the thread is entered into the monitor, other threads must be waiting. When one file is getting written, other thread should be waiting for reading. Only one thread can own a monitor at any given time. This line is very important thing to understand mutex or monitor, that is mutually exclusive lock. You have to understand, write down, learn this line. Only one thread can own a monitor at any given time. You can think a monitor as a small box. In that small box, when one thread has been entered, no other thread can go into a box. Okay, that box is called as monitor. Only when a thread acquires a lock or a monitor, it is said to have entered the monitor. All other threads attempting to enter the locked monitor will be suspended until the first thread exits the monitor. If all are still coming and trying to enter the monitor, those will be suspended until the first thread that is acquired the lock exits the monitor. These other threads are said to be waiting for the monitor. That is the waiting line or waiting queue. You can think it like that. The thread that owns a monitor can re-enter the same monitor if it so desires. Okay, if it is a high priority thread and all others are low priority thread, and if high priority has been resumed or has been relinquished the control over the monitor, and again for some reason it requires the monitor, besides make all the threads beside, keeping all the threads aside, it can go into the monitor again and again as much time as it is needed. If you have worked with synchronization when using other languages such as C, C++, you know that it can be a bit tricky to use because they themselves do not support synchronization. Synchronization is not inbuilt in C, C++, so it is very hard or very tricky to use synchronization in this case in C, C++. Instead, to synchronize threads, your programs need to utilize operating system primitive. Okay, so synchronize thread in that languages, your programs need to utilize operating system primitive. But Java implements synchronization inbuiltly through a language elements. Most of the complexity associated with synchronization has been eliminated. So you do not have to do anything if you want to achieve synchronization in Java language. That is why Java is called as simple as it can be. Okay, whatever complexity was there in C, C++ has been removed in Java. So what you have to do to achieve synchronization in Java, you just have to understand how synchronization is built and you have to build your program. Okay, there is no tricky, no irritating things in Java to achieve synchronization. It is as simple as that. You can synchronize your code either of two ways. Both involve the use of synchronized keyword that is inbuilt, and both are examined here. Using synchronized methods. Synchronization is very much easy in Java. What you have to do, you have to just understand what is synchronization and you have to learn how to implement synchronization. Okay. and you have to do nothing else. You have to just use that synchronization to achieve synchronization in your own Java application. All objects have their own implicit monitors associated with them. To enter the object's monitor, just call a method that has been modified with the synchronize keyword. While a thread is inside a synchronized method, all other threads that try to call it or any other synchronized method on the same instance have to wait outside. Okay, this is very important line. While one thread is inside the synchronized method, all other threads should be waiting. To exit the monitor and relinquish the control of the object to the next waiting thread, the owner of the monitor simply returns from the synchronized method. Okay, it will return or it will come out of the synchronized method and other next waiting thread will come inside. To understand the need for synchronization, let's begin with a simple example without synchronization. Okay, the following program has three simple classes. Call me has a single method named call. The call method takes a string parameter message. This method tries to print a message string inside of square brackets. The interesting thing to notice is that after call prints the opening bracket and message string, it calls the thread.sleep 1000 seconds, which pauses the current thread for 1 second. The constructor of the next class caller takes a reference to an instance of the call me and string which are stored in a target and message respectively. The constructor also creates a new thread, again that is the second thread that will call this object's run method, and the thread is started immediately. The run method of caller calls the call method on the target instance of call me passing the message string. Finally, the sync class starts by creating the single instance of call me and three instances of caller, each with a unique message string. The same instance of call me is passed to the each caller. What this description is telling us, it is very irritating. It is going overhead. So instead of explaining this, I will explain you the example. Okay, there is a one class that is call me. In that we are passing the message, and this is the call method of this call me. Here we are trying to print the message in square bracket. This is the opening square bracket and this is the message. In between, this is the interesting thing. In between we are slipping this thread 10,000, 1000 millisecond, that is 1 second, and interrupted exception has been caught. After that, square bracket is complete. This is the second caller object, second caller class. Second class message, target and thread. So caller has the object of call me. There is also one message here and one thread object here. Now parameterized constructor of caller takes two arguments, call me's target and string s. Target is equal to target, message is equal to s, and thread object has been instantiated. After that, thread is started. What is doing? It is doing in the run method. It is calling the call me's object, target dot call. Okay, so after target dot call, this will come here. This will print the square bracket, opening square bracket, and then message. Okay, so what is message over here? We have passed that over here. After that, our thread will sleep for 1000 millisecond, that is 1 second. After that, what will happen? That because of that in between sleep, output will not be printed as we have required. Now, what is the output? Call me target is equal to new call me. First, I have to print hello, then target synchronize word. So I have to print hello, then synchronize, then word, all in square bracket. Now, object 1 is waiting for join, object 2 is waiting for join, and 3 is also waiting for join. This is the output. Hello, synchronize, and word. For the first one, there is no opening and closing square bracket. For the second message, there is only opening square bracket and not closing square bracket. And here, there is the opening and closing both square brackets. This square brackets, remaining square brackets are printed in the last. Because of this sleep, the call method allows execution to switch to another thread. Okay, so two threads are created and Because of this sleep method, or the second thread that is waiting will get the control of the CPU, and because of this, not all of the thread messages will be printed. Okay, each time you are calling the caller, each time you are creating the caller object, what will happen? Each time new thread is created in caller. Okay, so each each thread is getting created, for each threading it is calling the call, it is calling the call method like t dot start. Okay, t dot start will print the message, but it is not printing the complete message at the same time. Okay, target dot call, t dot start will call the target dot call message, but since you are sleeping for 1000 millisecond, that is 1 second, other thread that is waiting, hello is printed. In between it is sleep for 1 second. In that 1 second, CPU will get the next thread that is synchronized. So its square bracket is remaining to be printed. That is, we have given after the sleep. We are printing this one, then message, and after sleeping, we are giving the closing square bracket. Because of this, all these messages are not printed properly, and which is not desirable. Here is the output. This is the not out. This is the output which is not required or not expected, and this is result in the mixed output of the three messages strings. Nothing exists to stop all these threads from calling the same method that is called on the same object at the same time. This is called as race condition. Who is taking the CPU time and who is printing first? This is the race condition, because the three threads that racing each other to complete the method. This example used sleep to make the effect repeatable and obvious. So sleep is used over here in this example. In most situations, a race condition is more subtle and less predictable because you can't be sure when the context which will occur. Okay, so every time race condition is more subtle because you are using only sleep method, because you don't know how much time when your thread will get the CPU time, for how much time it will be inside the CPU, and after how much time it will relinquish the control. So race condition is very much famous, very much general condition, and it is less predictable. You cannot say anything about this race condition, and you cannot say whether the expected output is occurring or not. This can cause a program to run right one time and wrong the next. Okay. To fix the preceding program, you must serialize access to call. That is, you must restrict access to only one thread at a time, so that when one thread is getting inside, all other threads must be waiting. First of all, opening square bracket will be printed, then hello will be printed, and after that its closing square bracket will be printed. And after that only the next two messages will be printed. So only one thread at a time, you should ensure that. To do this, you simply need to precede call's definition with the keyword synchronize. Synchronize void call string message. You just have to use this keyword, as simple as that. This prevents other threads from entering call while other thread is using it. After synchronize has been added to call, the output of program is hello synchronize void. So it is very important. Why? Because see, this is the output that was expected when multiple threads are running. So that's why it is very important in multi-threading synchronization. It is very important to understand it, learn it, and use it in your Java application. Anytime that you have a method or group of methods that manipulates the internal state of object in a multi-threaded situation, you should use the synchronize keyword to guard the state from race condition. Okay, so anytime that you want multiple methods that manipulate the internal state of the same object in a multi-threaded situation. Okay, so same method you are calling call method. There are multiple threads and there is only one method. All threads will be acquiring control on the same method. In that situation, you should precede that method with the keyword synchronize so that it will stop or it will avoid the rest condition. Once a thread enters any synchronized method on an instance, no other thread can enter any other synchronized method on the same instance. Okay. Once you are giving a synchronized keyword, what does that mean? All other threads must be waiting unless and until it relinquishes control from that method. Non-synchronized methods on that instance will continue to be callable. Okay. If there are multiple methods in your program, one is synchronized and other are non-synchronized, and threads are also calling that non-synchronized method, they will be called at any situation at any time. Okay, so their output is not predictable, but synchronized keywords methods, synchronized keyword, wherever you are using synchronized keyword, its output is always predictable. Then synchronized statement. While creating synchronized methods within a class that you create is an easy and effective means of achieving synchronization, it will not work in all cases. Okay, we have seen the synchronized method, but it is not it is not workable in all the cases. Why? Imagine that you want to synchronize access to objects of a class that was not designed for multi-threaded access. Okay, you are creating multiple objects of the same class. Okay, but those objects are not designed by you by for multi-threaded access. That is, the class does not use a synchronized method. Further, this class is not created by you but by a third party, and you do not have access to the source code. Thus, you can't add synchronize to the appropriate method within a class. So what should you do? How can access to an object of this class be synchronized? Fortunately, you simply put calls to methods defined by this class inside a synchronized block. Okay. The method definition is not your hand. You know that the objects are there, multiple objects are there of the same class, but those are not defined for the synchronized methods access. Okay, and this message or this complete program is not designed by you, and you don't have access to anything. What you will do? You simply put the call to method. Call the method inside synchronized block. So there are two ways. First is if everything is in your hand, what you will do? You will precede the method definition by synchronized keyword. And when anything is not in your hand, what you will do? You will simply put the methods call into the synchronized block. Synchronized object statements to be synchronized. Here object is a reference to the object being set. Synchronized. A synchronized block ensures that call to a method that is a member of object occurs only after the current thread has been successfully entered object's monitor. Okay. What does that mean? A synchronized block tells that a call to a method that is member of an object occurs only after current thread has successfully entered object's monitor. Alternative version of preceding example. Call me, public void call string message system.out.print message, and then 1 second sleep. Caller implements runnable. Runnable interface has been implemented. Call me target, thread object is created. Thread object is instantiated in the parameterized constructor, and synchronize calls to call. Public void run synchronize target. This is the block. Target is the object. Okay. So target that we have initialized in the parameterized constructor. While we will calling, creating the caller object, we will pass this call me target object, and this object will be passed over here to be synchronized. So one object will get access to that method at the same time. Unless and until that object do not comes out, like hello has not been printed, other message hello synchronized word. Hello, unless and until hello is not coming out, synchronize cannot go inside. Then synchronize will come Unless and until synchronized object task is not finished, word cannot go inside. And after synchronize relinquish the control, word come inside and it will print the message. And all the threads has been done. Now wait for the threads to end try. Object 1 joins, wait for join, object 2, wait for join, object 3, wait for join. So every run in every for every object run method will synchronize the object that has been passed. Same object has been passed here. Okay. Then interrupted exception has been caught. Here call method is not modified by the synchronize keyword. Okay. We have not written synchronize here before call method. Instead, the synchronize statement is used inside caller's run method. This causes the same correct output as preceding example because each thread waits for the prior one to finish before proceeding. Now we will see inter-thread communication. The preceding examples unconditionally block other threads from asynchronous access to certain methods. Okay, there are multiple threads running, but they unconditionally block each other. This use of implicit monitors in Java object is powerful, but you can achieve more subtle level of control through the inter-process communication, and especially is in Java. Multithreading replaces event to programming by dividing your tasks into discrete logical units. Threads also provide a secondary benefit. They do away with polling. Okay. Multithreading has been achieved how? By dividing your task into discrete logical units, and threads also provide a secondary benefit, that is polling. Polling is usually implemented by a loop that is used to check some condition repeatedly. Once the condition is true, appropriate action is taken. Okay. So again and again check. If this file has been completed writing, yes, no. After 1 second, again check. If this file has been completed writing, no. After 1 second, again check. If this file has been completed writing, I want to read it, no. Again after 1 second, again it will check. If this file has been completed writing, yes. So come out, I have to go inside to read that file. So this wastes the CPU time. For 4 seconds, CPU time has been wasted. For example, consider the classic queuing problem where one thread is producing some data and other is consuming it. Suppose the producer has to wait until the consumer is finished before it generates more data. In a polling system, consumer would waste many CPU cycles while it waited for the producer to produce. Okay, consumer and producer are there, and it would waste many CPU cycles while it waited for the producer to produce. Once the producer was finished, it would start polling, wasting more CPU cycles waiting for the consumer to finish, and so on. Clearly, this situation is undesirable. To avoid polling, Java provides elegant interprocess communication mechanism while wait, notify, and notify all methods. And though all these methods are implemented as final methods in objects, so all classes have them. All three methods can be called only from within a synchronized context. Although conceptually advanced from the computer science perspective, the rules for using these methods are actually quite simple. Okay. So what is the rule? Those are final methods, and those can be called only from within a synchronized context. The rules for using these methods are simple. Wait tells the calling thread to give up on the monitor and go to sleep until some other threads enter the same monitor and calls notify. Notify wakes up a thread and called wait on the same object. Notify all wakes up all the threads that called wait on the same object. One of the threads will be granted access at one time. These methods are declared within object as shown here: final void wait, close interrupt exception, final void notify, and final void notify all. In this way, we have seen some points in this session. In the next session, we will complete all the remaining topics in multithreading, and we will start with the practical part. All that whatever we have understood in multithreading theory, we will be implementing in practical. So you don't have to worry. You have to just learn things. When we will be practicing the practical sessions, you will get it more clear. And when you will practice it at home by yourself, it will be more easy for you to implement Java applications. So meet you in the next session. Thank you so much.